This week, we are going to start predicate logic, which is a little bit more powerful than propositional logic, because now instead of just looking at an entire sentence, we can actually break noun phrases into parts, adjective phrases into parts. We can talk about all these parts individually. So to demonstrate this, imagine in propositional logic that we had two sentences that differed only in their subject. So example 1, Beethoven naps, Mozart naps. We have to give each of these different letters because they represent different propositions. So we could call B, Beethoven naps, M, Mozart naps. But linguistically, the only difference between these two sentences is a difference in subject. The verb is the same, so you can imagine that in our translation, we should have at least some similarity into whatever logic system we're using. There should be some consistency of napping. That should be representative in both of those, and there's only a difference in subject. So that subject part should be a little bit different from what's happening with the verb. Now, predicate logic allows us to do that. We can now decompose sentences into predicates and individuals. So, for example, Beethoven naps, we can write this as naps with Beethoven as an argument. So, or we could just shorten this to N with B as an argument, which basically means that we have the verb or that we have the relation out front, and then we have the individuals or our NPs or whatever we're going to fill in there inside of our little relation there, or inside of our function. We can think of this as a function too. And so as you can see, the difference now between Beethoven naps and Mozart naps is just what the subject is. The verb, naps, is now the same. It's represented in both of our translations. Now, there's two different ways that we can do this. I like to write out the entire word, so naps Beethoven, if I'm doing something with real sentences, just because that way it's very explicit what I'm talking about. But we can always shorten these. So we could call this NB, and we could call this NM for Beethoven naps and Mozart naps. But if you do this, you have to specify a key. So that way we know exactly what N means, we know what M means, we know what B means. So you have a choice how you want to do it in this course. Usually when things are just generic, I just use one letter, but when we have actual sentences, I write out the complete thing. That way you can sort of read it as you go. Now just keep that in mind. If you use short form, please specify all of your keys. So here's what the system allows us to do, because we can do more than just decompose things into verbs and predicates. We can also add in quantifiers and determiners. And we'll talk about how we do translation in the video next week, so don't worry too much about how this is done right now. This is just about explaining and showing you what we can do. So we're now able to handle quantifiers and pronouns. So for example, the sentence, every cat is sleeping. Okay, every cat is sleeping. Well, if we think about what this means that if we have the set of all of our cats, that set is a subset of everything that is sleeping. So basically, the translation for this would be every single cat, all of the things that are cats, are also sleeping. So we can translate this with quantifiers. So we have this new quantifier for all x. This is an upside down A, which means universal. So this means every. So for all x, if x is a cat, then x is sleeping. That means every cat is sleeping. If we have the sentence, some girl likes David, well, let me just shorten that diagram up. Every girl likes David, or sorry, let's just say some girl likes David. That is what we're going for. Okay, so there's a set of girls here. There is a set of people who like David, and some girl likes David means that there's some person in the intersection of these two. So there's something that is a girl, and there's something that likes David, and those happen to be the same thing. So we have another new quantifier here that we can use in translation. This is the backwards E, and this is called the existential. So this just means or some, or at least one. So to say some girl likes David, we could say, there is something out there, variable x, such that that x is a girl, and that x likes David. So we can also see here that a predicate likes David, likes xy, it has a subject and has an object, and we can represent those here. We can represent the subject, and we have the object here, which is David. So this is the power of predicate logic. And if we don't have a quantifier out front, if we don't have a universal or an existential, and we still have a variable like x, then when this is what's called free, we'll talk about that in scope in the next video, we refer to this as a pronoun. So she likes David could be represented as likes X David. So we could read this as X likes David, and we just specify sort of the constraints on X. So if we say she likes David, then X is some individual whose conceptual gender is female. Conceptual gender is a term that was introduced by Ackerman quite recently. I don't know if it's widespread yet, but conceptual just means this is the presentation of the person. So however you want to define gender in linguistics, that's really fine. It's up to you. This is just the new term that has come into use. So perhaps we'll see it as we go forward over the next few years and how it evolves. Okay. So this is a little bit important to talking about the syntax of predicate logic, and I just want to talk about this now. We're going to revisit it when we do translations again. But whenever we have a quantifier, so words like every, all, some, most, many, we can divide these into two different components. So every bird is flying. Usually what we do, and this really helps with predicate logic translation, and I don't ever see this really anywhere else. So I'm surprised this isn't a very widespread method. Maybe you've seen this before, maybe not. Every single quantified noun phrase, we can pull this out. We can pull this out. So every bird, well, it's every something that is a bird. So we just give it a little subscript, like this is our X. Every bird, this is a quantified thing. We give this a variable that associates with it. And we can bring this out. We can bring this out and we can paraphrase. So we can say every bird X, and we can paraphrase this last bit is flying, and we can change it to it is flying, and we can subscript whatever it is. So it's as if we're co-indexing, as if we're making a connection between the subject pronoun and whatever we pulled out. Now this might seem a little bit weird, but when you translate these things and break things apart, it just works. So every bird, well, every is a quantifier, bird is a noun, so we can separate these into their two different categories, and we subscript them to know they're the same, and then we could just do a direct translation into predicate logic. So we'll see this in action again next week when we actually translate things. I just want to show you ahead what this is. Okay. So this last line here talks a little bit about what it is. So when we pull things out, essentially what we're doing is we're restricting the domain of things. So every bird X, it is flying. We're basically restricting what it is. So we're restricting and saying that it has to be a bird. Again, we'll talk more about that a little bit next week. I just want to show you exactly what these translations look like and a very quick overview of the process, just so that way it's familiar next week. Okay, here is our syntax of PC. Here is what we have now, because we have a little bit more than we did in propositional logic. So what we have are constants, A, B, C, and D. So these are what we use for names. We can either use A, B, C, D, or we can use actual names. So we could have, for instance, Kate as a constant. A constant just means it refers to someone in the real world. It is a constant thing. If you say Kate, that refers to Kate, and that always refers to Kate. We have these different types of terms as well called variables. These are our pronouns when they're left alone, but these are also used for binding, which we'll talk about in the next video. So these are the things that can be bound. And the term binding in predicate logic, and logic in general, is actually very similar to what binding means in syntax. In fact, it's really exactly the same because the systems are the same. We use trees, we use C command, we use those same terms. Okay, now instead of propositions, P, Q, and R, we now have predicate. So predicates, P, Q, R. And you can have predicates that are zero place. So you could have, say, P for it rains. Well, maybe I might translate that as R. This is called an expletive it, so that is not actually an argument. It doesn't have content like Kate rains. Well, that doesn't make any sense, but it rains. That's a zero place predicate. We have one place predicates. like sleeps is happy or eats. We've seen these before, so we could write this as, say, sleeps X. Just looks just like a unary relation. We have two-place predicates, so these are transitive verbs. So likes, we call this two-place because it needs a subject and an object, so it's XY. And we have three-place predicates, XYZ. So in the homework, I think you did introduces, but there's other ditransitive verbs like gives, which takes an X, Y, and a Z. So X gives Y to Z. We have a new connective, which is the identity. This is the equals. This is essentially is. We'll see how that's done a little bit later when we talk about some more complicated translations, but we won't introduce it in our earlier translations because we typically don't have too many straightforward ones that use them. The connectives of predicate logic are the same as the connectives of propositional logic, and we now have two new quantifiers. So we have the upside down A, which means for all, and we have the backwards E, which means exists. So for all meaning every, and exists meaning at least one. So how do we put these together? We have rules. What is a well-formed formula? Well, any predicate is a well-formed formula. So you can have a 0 place, a 1 place, a 2 place. So let's say we have p, x, y. This is a well-formed formula, provided that x and y are terms and p is a predicate. So we can split this up in our tree into three components, the predicate itself and the two variables that we have. This works the same even if these are not variables but are constants. So PAB also splits up into PAB. If we were to have something a little bit longer, so PXY, ZW, then we could split this up into 5 branches. So yes, that does look a little different than what you would see in normal syntax, but this is how we break up predicates into their components. If we have a well-formed formula that is T and say P, so T equals P, we can split this up into T equals and P, where T is the same as P. As far as alpha and beta, if those are whoops in predicate logic, then the same whoops that we had in propositional logic are the same. So for example, let me just clear up some space here. If we have, say, px and qxy, well, this is a formula that splits into px, the conjunction, and then qxy. And then these px, qxy would then split into components. So that's how we do a syntactic tree for that. Okay, I'm going to keep this one on the page because this covers pretty much all of the rules that we've seen so far. And finally, with our new quantifiers, all x exists in x, we can take any well-formed formula. So let's take this. Let's just take px. And what we can do is we can put a quantifier with a variable in front of it. It must have a variable. So we could do something like exists in x, px. And this would split up into two components, the existential and then px, and then this, of course, would split into two components, p and x. So that's one example that we could have. Or if we have something like qxy and lx, just for example, we could do it with the universal. So we could do for all, and let's do y for this sake. We could do all y, qxy and lx. And then we break this up into its two components, the quantifier and then whatever comes afterwards. And then that would then split into further components. But we don't have to use a variable that's in our formula. We could have a totally different variable. So we could say, for instance, for all p, qxy and lx, split that up into for all p, qxy and lx, and this is also valid. And nothing else is a well-formed formula in predicate logic. So this is sort of how we do trees. This is how we break things apart. We'll talk about what these mean in terms of English next week. I just want to focus on some of the structural things because we just had a test this week, so let's not do too much learning. Anyways, so like I showed you before, all of these well-formed formulas can be broken up into syntactic trees. So here we have exists in x, mjx. So we can split up the quantifier with the predicate, and then we break down the predicate into its components. Now, we can make these things more complex. So we could say and for all y, m, y, y. This is also perfectly valid. In this case, what we would do, instead of breaking it up directly into existEnX, MJX, of course we know this is ternary branching, so we'd have 3 different components that come off of it. We'd have existEnX, MJX on the left, and then for all y, MYY on the right. Actually, what I should do, because I wrote it out, I should probably show you how this works. MJX and for all y, MYY. Now I use square brackets after quantifiers just because I find it easier to see how long the quantifier stretches, at least what it scopes over. We'll talk about that term next video. But you can use really whatever brackets you want. It doesn't matter. I think the square brackets just make it easier to read. Anyway, so this would split into 3 components, existEnX, MJX, and for all y, MYY. And then this would split as normal. So existEnX, MJX on the left, MJX get broken up, and then on the right we'd have for all y, MYY, and this would split up into 3 components, M, Y, and Y. So we can also see with this example, it's perfectly okay to have the same variable occur twice. This just means that this is a reflexive situation. If you remember from week 3 when we talked about reflexive, symmetric, and transitive properties, it just means that y m's y or y m's itself, whatever m happens to mean here. So to finish up this video, we'll do a few practice questions. Determine whether each one is a well-formed formula or not. If it is a well-formed formula, draw its tree. So you can pause the video, try it yourself, and let's go. Okay, first one. This is not a well-formed formula because we have exists for all x. We need something after the existential. We need like a y or something. We need some variable. Whatever that variable is, it's fine. We just need something. Another thing that gives it away is that we have 2 predicates here, PB and RC, but we need like an and or an or an arrow or an if and only if. We need some sort of conjunction between the 2 in order for it to be well-formed. So A is not well-formed. B is well-formed. So let's draw this one out. So we have for all x, px arrow exists a y such that qxy and pz. And we have 2 outer brackets. Okay, so the first thing we do is we see a universal quantifier, all x, outside the entire thing, so we can follow the brackets and we can see how long it extends. It extends to the very end. So the first thing we do is we break it up into its components for all x, and then we're left with px arrow exists a y, qxy, and pz. Okay, at this point we have a conditional connecting 2 things. We have px on the left, and exists a y, qxy, and pz on the right. So we can split this into 3 components, px, the arrow, and there exists a y such that qxy and pz. Fantastic. Okay, the left we have px. We can split this up into 2 components, the p and the x. Notice how we do not do that for the quantifier, so we do not split those up into for all and x. It's just a convention. The arrow doesn't need to be broken down anymore. We see exists a y. We see an outer bracket, so we see where that closes, and that's how we break this one up. So there is exists a y. Then we're left with qxy and pz on the right. Okay, qxy and pz, this splits up into 3 components, qx and y, the conjunction, and then pz. Finally, these predicates all break down into their individual components, so qxy breaks down into qx and y, and pz breaks down into p and z. So this is the syntactic tree for the second question here, 6b, which is a well-formed formula. So now that we have that, I'm going to shrink it a little bit and give ourselves some room for the next question. So I'll put this right down here, and I'll label this as B. Now let's do C. C is also well-formed. It follows the rules, and we see the identity operator in there. So although we're not using it for translation right now, it's good to recognize where it is appropriate, so that way when we do see it later, we are not caught off guard. So this time, instead of using x's and y's, I've used x1 and x2. It really doesn't make a difference. I could use y instead of x2, but Sometimes you might need more than 26 variables. Well, you won't in this course, but sometimes you do. And when you do, it's good to use subscripted numbers instead of just going through all the letters and then doing it again. Okay, all x1, all x2, px1, x2, and j equals b. So all x1 scopes over the entire thing, as you can see with the brackets. So we break this up into two components, all x1 on the left, and then on the right, we're left with all x2. Then we have px1, x2, and j equals b. In my head, this will always be written as Justin equals Bieber. I have no idea why, but if it's stuck in your head now too, thank you for suffering along with me. Okay, break down this next part. All x2, px1, x2, and j equals b. The square brackets cover the entire thing, so we can separate all x2, and the right side, which is px1, x2, and j equals b. In reality, the translation would be something like John is Bill, or something like that. Two individuals are the same. Okay, px1, x2, and j equals b. Split this up into three components joined by the connective and. So this is px1, x2, and j equals b. Okay, our predicate can be broken up into px1, x2, and our j equals b can be broken up into j equals and b. So that's the syntactic tree for C. Let me check. Okay, yes, that is the end of this video. So this is all about the structure and sort of why we have the system that we do. If there's any questions, there's always discussion board or email, and I'll get back to you when I can.